In this video we're going to look at the distribution known as the continuous uniform distribution. Suppose then in a large city the number 27 bus runs day and night, and the timetable states that the bus runs every 20 minutes. A survey was conducted over a period of 120 hours at a bus stop on the route, and the 360 time gaps between consecutive number 27 buses were recorded. The results are shown in the histogram, and the summary statistics are shown in the table. Now the total area of the histogram will be 360 because there are 360 observations here. Now what we want to try and do is produce a probability model for the gap, which we're going to denote by the random variable t, which is going to be measured in minutes, between consecutive number 27 buses. So if we divide the frequency densities by 360, our histogram will become a relative frequency histogram, or a normalized histogram. So the only thing we've done is we've divided all of the frequency densities by 360, which means the area under the graph now, instead of being 360, will just become 1. Now looking at the graph and at the summary data, it looks as if first of all, the data is concentrated on the interval from 17 up to 23. So it's concentrated over the interval from 17 to 23. That the data is fairly evenly spread through the interval. And the data looks as if it could be symmetrically distributed about the midpoint of the interval, which is 20 minutes. These facts then suggest that the probability distribution for our random variable capital T might have a probability density function which looks like a constant value, which we'll call k, between 17 and 23, and it's 0 everywhere else. So expressing that as a formula, we can say that f of t is equal to k for any value of t in the interval 17 to 23, and it's equal to 0 otherwise. We know that the area underneath the graph has got to equal 1, so we can say that 23 take away 17, which is the base, which is 6, times by k must equal 1, so k must equal 1/6. So we now have a possible probability density function for our random variable t. If this is the case, then we say that t has the continuous uniform distribution on the interval from 17 to 23. So assuming that this is the case and that we can model the gap between successive number 27 buses by the continuous uniform distribution over the interval 17 to 23, we're going to calculate the probability the gap between successive buses will be less than 21 minutes. We're going to find the mean and median gap between successive buses. We'll find the quartiles and the interquartile range of the gap between successive buses, and we'll find whether outlier values for the gap between successive buses are possible using this model. And we're going to then discuss the suitability of this model for all circumstances of the bus service. So here's the probability density function for capital T again. The first thing we're trying to work out is the probability that the gap between successive buses will be less than 21 minutes, and that is the shaded area. That's nice and easy to work out because the base of this rectangle has width 4, the height of the rectangle is 1/6, so we've got 4 times a sixth, which is 2/3. So the model is giving a probability of 2/3 that the gap between successive buses will be less than 21 minutes. Since the distribution is symmetrical about t equals 20, then we've got the mean is equal to 20 and the median is equal to 20 minutes. If we let Q1 be the lower quartile of the distribution, then we know the probability that t is less than or equal to Q1 is going to be equal to 0.25. In other words, the probability to the left of Q1 must be equal to 0.25. So in this case, we know the area is 0.25. We've got the base of the shaded area has width Q1 take away 17, and the rectangle has height 1/6. So we can say that 0.25 must be equal to 1/6 times by Q1 minus 17. So we've got Q1 minus 17 must equal 1.5, so Q1 must equal 18.5. A similar argument, or indeed symmetry, will give us that Q3, the upper quartile, must be 21.5 minutes. So the interquartile range for this distribution is going to be 21.5 take away 18.5, which is 3 minutes. Now we need to recall from M2 that the lower fence for a distribution is the value of the lower quartile minus 1.5 times the interquartile range, and the upper fence for a distribution is the value of the upper quartile plus 1.5 times the interquartile range. And then any observation that is less than the lower fence or greater than the upper fence is defined to be an outlier. So in this case then, the lower fence is going to be Q1 take away 1.5 times the interquartile range, so that's 18.5, take away 1.5 times 3, which gives me 14. The upper fence is going to be Q3 plus 1.5 times the interquartile range, so that is 21.5 plus 1.5 times 3, which is 21.5 plus 4.5, which is 26. So the outliers will be any observation less than 14 or any observation bigger than 26. But we know that the random variable t is only taking values between 17 and 23. So there are no values less than 14 or greater than 26. So there are definitely no outliers. Now that is slightly suspicious because in times of bad weather or heavy traffic, the gap between the buses may be much greater than those predicted by our model. So in times of bad weather or heavy traffic, this model may well be inappropriate. So let's move on to a second example. In a game, players select sticks at random from a box containing a large number of sticks of different lengths. The length L of a randomly chosen stick from this box has the continuous uniform distribution over the interval 14 to 19. A stick is chosen at random from the box. The first thing we've got to do is find out the probability that the stick is less than 15.5 centimeters long. Since L has the continuous uniform distribution over the interval 14 to 19, we know that the distribution looks like a constant function between 14 and 19 and 0 everywhere else. The area under the graph has got to equal 1, so the base of this rectangle is going to be 5 units across, so the height, in order to make the area underneath the graph equal to 1, must be 1/5. the probability that the stick is shorter than 15.5 centimeters, then it's going to be the area underneath the graph from 15.5 down to 14. So that gives me a rectangle whose base is 1.5, whose height is 1/5. So we've got 1.5 times by 1/5, which gives me 0.3. Now, a player will win a prize in the game if, when she draws 4 sticks out of the box, the length of the shortest stick is less than 15.5 centimeters. We've got to find the probability of her winning a prize in this particular game. So, the probability she wins a prize is the probability at least one stick with a length less than 15.5 centimeters, which is the same thing as 1 minus the probability that there are no sticks with a length of less than 15.5 centimeters, which, now the probability that a stick is less than 15.5 centimeters is 0.3, so the probability that that a stick hasn't got a length less than 15.5 will be 0.7. So the probability that none of the sticks have a length less than 15.5 is going to be 0.7 to the power 4. So the probability she wins the prize is 1 minus 0.7 to the power 4, which is 0.7599. Now, in general, if x has the continuous uniform distribution on the interval a up to b, then the probability density function, or the probability histogram for x, looks like the diagram we've got here. So it takes a constant value between a and b, and that constant value is 1 over b minus a, which ensures that the area underneath the graph is equal to 1. Probabilities can be worked out by the area under the graph. So if we want the probability that we're between the value c and the value d, the base of our rectangle will have a length of d minus c. So we've got d minus c times by the height of the rectangle, which is 1 over b minus a. So that just gives me d minus c over b minus a. Since the distribution is symmetrical about a plus b over 2, we can say the expected value, or the mean of x, which is going to be the same as the median of x, is going to be equal to a plus b over 2. It can be shown, although only those of you who go on and do Further Maths Unit 2 will see the justification of this, that the variance for the continuous uniform distribution is given by the formula 1/12 of b minus a all squared. Since the distribution is constant between a and b, we can say that the lower quartile is 1/4 of the way from a to b, and 1/4 of the way from a to b is going to be a plus 1/4 of b minus a, which simplifies to 3/4 a plus 1/4 b. And a similar calculation gives the upper quartile as being 1/4 a plus 3/4 b. So the interquartile range is always going to be a half of b minus a. If we have a look at the fences for the distribution, the upper fence for it is Q3 plus 1.5 times the interquartile range. That simplifies to 3 over 2b minus a half a. We know that b is bigger than a, so therefore 1.5b take away a half a is definitely bigger than b, which is the maximum value that x can take. Similarly, the lower fence is definitely smaller than the minimum value that x can take. So the continuous uniform distribution definitely has no outliers. So a final example then. We have a science teacher believes the time t minutes for a randomly chosen student to complete an experiment has the continuous uniform distribution with a median of 35 and a standard deviation of root 48. We've got to first of all write down the mean time for a randomly chosen student to complete this experiment. Well, if it's got the continuous uniform distribution, it's certainly symmetric, so the mean time is the same as the median time, so the mean time must be 35 minutes. Now, the next part says we've got to find the probability that a randomly chosen student will complete this experiment in less than 40 minutes. Now, we need to know what the interval is that t takes the continuous uniform distribution over. So what we're going to have to say is, let's suppose that t is uniformly distributed over the interval a to b. If that is the case, then we know that the mean value of t, which is 35, has got to be equal to a plus b over 2. In other words, we know that a plus b must equal 70. We also know that the variance is 1/12 of b minus a squared. Now the variance is simply the standard deviation squared. So if the standard deviation is root 48, the variance must be 48. So we've got the variance, 1/12 b minus a squared, must be 48. In other words, we've got b minus a squared is 576. So b minus a must be 24. We know it must be 24, not minus 24, because we know b is bigger than a. So I've got a pair of simultaneous equations for a and b. We know that a plus b is 70. We know that b minus a is 24. So solving the simultaneous equations, we've got b is 47 and a is 23. So we now know that t has the uniform distribution over the interval from 23 to 47. That means that we could say that the probability the randomly chosen student will complete this experiment in less than 40 minutes is going to be the shaded area there. Base of that shaded area has width 17. The height is 1/24. So we have got the shaded area is 17 times by 1/24. So that gives me 17/24. Find the probability that at least 10 out of a class of 15 students will complete the experiment in less than 40 minutes. What additional assumption does this part of the question require? Well, let y be the number of students in the class who complete the experiment in less than 40 minutes. Then y can be modelled by the binomial distribution with n equals 15 and p equals 17/24, provided we regard the students in the class as working independently of each other and also having the same probability that they will complete the task in less than 40 minutes. Given that, then, what we want is the probability that y is at least 10, so that's y is greater than or equal to 10. That's 1 minus the probability that y is less than or equal to 9, because we're dealing with a binomial distribution which is discrete, and we can use our calculator to obtain that probability, which is 0.2542. So we've got the probability that y is greater than or equal to 10 is 1 minus the probability that y is less than or equal to 9, which is 1 minus 0.2542, which gives me 0.7458. That concludes our look at the continuous uniform distribution.